Hello guys, today we'll be going over function counting in the AMI. So I need to scroll first. So it's really hard to explain without an example. So I suppose I'll start with an example. So this is from the 2014 AMI one. This is problem 12, and it reads, I should probably annotate now. Let A equals 1, 2, 3, 4, and F and G be randomly chosen, not necessarily distinct functions from A to A. The probability that the range of F and the range of G are disjoint is M over N, where M and N are relatively prime positive integers. Find N. Again, feel free to pause and ponder. So I'm assuming that you're done pausing and pondering, and I'll go through the walkthrough. So what is probability? We want the number of favorable outcomes over the number of possible outcomes. There 4 to the power of 4 squared equals 4 to the 8 possible outcomes. And this is because, so the possible outcomes is like choosing F and G, just like choosing random functions. And they go from 1, 2, 3, 4 to 1, 2, 3, 4. So like choosing a function, how many functions are there? Well, like this 1 can go to 1, 2, 3, 4, so 4 choices. This 2 can go to 1, 2, 3, 4, 4 choices, etc. So 4 to the power of 4 for a function. And then since you're choosing F and G, you have to square that. So 4 to the power of 8. Now, for the favorable outcomes, we do casework on the size of the range of F. So first, if the range has size 1, there are 4 choices. There are 4 choices for what the range is, 1 choice for what F is, and 3 to 4 choices for what G is. So basically, it's this means that the range has size 1. So F is a constant function. Everything maps to one thing. There's 4 choices for what it will map to, right? Like let's say they all go to 1, they all go to 2, they all go to 3, they all go to 4. So 4 choices. Then 1 choice for what F is, right? Because like for a given range, which is like, let's say like 1 is a range, then they all just all have to go to 1. So there's just 1 choice there. And 3 to 4 choices for G is, because G, like let's say you pick a random element, then G is any function going from 1, 2, 3, 4 to some 3 element subset. Right? And 1 can go 3 choices, 2 has 3 choices, 3 has 3 choices, 4 has 3 choices, etc. So it's 3 to 4 choices. So 4 times 3 to the 4. And then, when I scroll down, it like moves my annotations as well. So hang on, so first I'm just gonna initially scroll down to here, and then I'm going to annotate now. Where's the annotation button? Oh yeah, finally it's here. So let's clear all drawings. And okay, so as I said before, this is 4 times 3 to the 4. Now if the range has size 2, first we gotta pick what the range is, right? So let's say the range is 1, 1, 2. So like for example, it's like without loss of generality, but we have to multiply this by 4 choose 2 because we choose the range and 4 choose 2 equals 6 ways. 6 times, and 36 choices for what F is. I mean, no, 14 choices. I was reading this. So 14 choices for what F is, right? So something like this, right? And how many choices are there for F? Well, okay, so initial count. 1 can go to 1, 2, 2 can go to 1, 2, 3 can go to 1, 2, 4 can go to 1, 2, so you get 2 to the 4. But you have to subtract the things where 1, 2, 3, 4 all go to 1, and 1, 2, 3, 4 all go to 2. And those are counted in this. But the range would then just be 1 or 2, not 1, 2. So we have to subtract those out. So there's two of them, the ones that go to 1 and one that go to 2. So 2 to the 4 minus 2, which is 14. So 6 times 14. And 1 to the 4 shows for what G is. No, 2 to the 4. I keep on reading this. Never mind, because it's like the bottommost thing. And 2 to the 4 choices for what G is. Because, like, so this is the range of F. The range of G can be any subset of this. So 1, 2, 3, 4 to some two element subset. Then for each 1, 2, 3, 4, there's two ways to go from 1 to this. Like, because like there's 2 options for 1, 2 options for 2, 2 options for 3, 2 options for 4. So 2 to the power 4. And this gives 6 times 4 times 2 to the power 4. If the range has size 3, then there's 4 choices for what the range is, right? So 1, 2, 3, 4. 1, 2, 3, 4. So the range could be any 3 element subset of 1, 2, 3, 4. So 4 choose 3 or just 4. So 4 choices for what the range is. So let's say the range is 1, 2, 3. Then 36 choices for what F is. And this is actually a bit involved. No. So basically, let's do a base count. For 1, there are 3 choices. For 2, there are 3 choices. For 3, there are 3 choices. There's 4. There are 3 choices. So 3 to the 4, right? We have to subtract when the range is like 1, 2, 1, 3, 2, 3. So you have to subtract those 3 cases, and that's when the range is 2 elements. So 2 to the 4. But you also like count. Let's say like the one to like the range is just like 1, right? So how many times did you count this? So like you counted it in the 1, 2, 3 case once. You counted it in the 1, 2 case once, I think. You counted this in the 1, 2, no, 1, 3 case. No, yeah, you counted this on the 1, 3 case once. So wait, what am I doing again? I think you just hang on. 1, 2 case once. And wait, so oh yeah, but we don't want to include this. That's why we add 1 to it. So we got to add back the case where it's just like 1 element, and there's 3 of them, right? There's 3 of the 1 element things, and the number of choices is just 1 because like they don't all map to it. And this becomes 81 minus 48 plus 3, 84 minus 48. You can subtract that and get 36. So 4 times 36. And 1 choice for what G is, because G is just like 1, 2, 3, 4 to like some 1 element thing, and 1 choice for 1, 2, 3, and 4. So 1. Well, this is 4 times 36. We've exhausted all cases because like if the range is size 4, then I mean G can't be disjoint from that unless the range of G is empty. But that's impossible, right? Because like G of 1 has to be something. It can't be empty. So anyways, the number of possible outcomes or the number of favorable outcomes is 4 times 3 to the 4 plus 6. Oh, I also meant 14. Oops, right? Yeah, I wrote 14 there. Plus 6 times 14 times 2 to the 4 plus 4 times 36 and divided by the number of outcomes, 4 to the 8. Now divide everything by 4, you get 3 to the 4. Divide this by 2, divide this by 2. 3 times 7 times 2 to the 4 plus 3 to the 6 over 4 to the 8. So what is the numerator? Well, we can compute that out. Oh, wait, no, this is 36. I need to work on my handwriting. Oh, 3 to 6. So yeah, so the numerator becomes 16. So this becomes 16 times 21. 210, 126, 336. 336 plus 36 is 372, and 372 plus 81 is 453. And since this is odd in the denominator, the power of 2, it follows that since it asked for m, the answer is 453. Yep. And yeah, it asked for m. So I will clear my annotations. Where's the annotate, clear. Okay. So here's another example. Let a equals 1, 2, 3, 4, 5, 6, 7, and let n be the number of functions from set A to set A, such that f of x is a constant function. Find the remainder when n is divided by 1000. So I'll let you pause and ponder for a bit. You can pause the video if you want. I'm assuming you're done with that, so I'll move on. Oops. Yeah, okay. So, should I zoom out? Oops. I tried to press command minus, but that didn't zoom out. Okay, I didn't know you can't do that. Okay, so first of all, I want to like see the pro. Maybe I'll just like get rid of this because I can internalize it. Anyways, so basically, first of all, we draw it out, right? 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. 1, 2. Oh, wait, this isn't. Okay, so f of x is a constant function. So some random path, but this must end up at like after like the one, let's say 1 goes to 4, then goes to 3, 2 goes to 4, 2 goes to like 5, then goes to 3. They must all end up at like 3 or like 1 or 7. So first let's multiply by 7 and then assume that it ends up at 1. Right. So these don't matter. Now you can conclude something. First of all, let's say you can conclude that f of 1 equals 1. And why is this true? Let's say f of 1 was anything other than 1, right? Let's say f of 1 was like 3, for example. Then this has to go to 1, right? No matter what, because that's what the constraint of the problem is. This means f of 3 is 1. However, this means that f of 3 is 1. But f of 1 is 3, so this just goes to 3. But that's not allowed. Thus, f of 1 must be 1. Okay. And so f of 1 equals 1, and f of 1 equals 1 again. Now we can do casework on the number of things that go to 1 directly. What do I mean by that? Let's say like 3 goes to f of 3 equals 1. So then it just goes to 1 directly. That's what I mean. So we're doing casework. Casework on number of k, number of k with f of something equals 1. And okay, so let's say k is 1, right? Then, for example, let the lucky number from 2 to 7 that goes to 1. Let we can like, how many choices are there for that? 1, 2, 3, 4, 5, 6. 6 choices. So without loss of generality, to make life easier, is there a eraser here? Yeah. We can drawing the eraser. Okay. Draw. Okay. So f of 2 equals 1. Right. And now let's consider these things, right? These can't go to another of these things. You know why? Because if let's say like 3 goes to like 5, right? Then this 5 goes to 1, right? But the only thing that goes to 1 is 2. So 3 to 7 can't map to 3 to 7. So it must, and they can't map to 1 either, right? Because that would contradict our condition. So these must all map to 2. And there's only one way to do that. So just 1, 6. K equals 2. Let's say there's 2 things that map to 1. And the way we can choose them is 6 choose 2. Now, by the same logic, this 4, 5, 6, 7, they must all map to things in 2, 3. So how do we count them? Well, 4 has 2 choices, 5 has 2 choices, 6 has 2 choices, 7 has 2 choices. So 2 to the power of 4, I believe. This is 15 times 16. This is 30 times 8, which is 240. I'll underline these because these are important. And so yeah, I think importantly in general in the Amy, if you're like bashing or like doing something close to bashing, you should probably be organized because it's really easy to make a silly. If k equals 3, then that lets me know really 2, 3, 4 go to 1. Then 6 choose 3 ways to choose the things, right? And 4, 5, 5, 6, 7, they must go to 2, 3, 4. So 3 choices, right? And there's 3 of 5, 6, 7, though 3 cubed, which is 6 times 5 times 4 over 3 times 2 is 20. And 3 cubed is just 27. So this is 540. K equals 4. So this goes here too. 6 choose 4 ways. And 6 and 7, they must map to 2 to 5. So 4 choices and 2 things, so 4 squared. And this is 15 times 16, which is 240. Same thing as k equals 2, but it's just a coincidence, 2 to the 4th, 4 squared. K equals 5. Another one. This is getting kind of messy. This drawing. 6 choose 5 ways to pick. No, 7, right? This must map to either 2, 3, 4, 5, 6. That's 6 choices. Wait, no. Is it 2, 3, 4, 5? Oh, yeah, that's 5 choices. I can't count. Apparently, there are 6 numbers from 2 to 6. Okay, so 6 times 5 is 30. And finally, k equals 6. And just one way to do it. Right, one way to choose it, just 6, 6, and just 1. So add them all up. 6 plus 240 is 246. 246 plus 540 is 786. 786 plus 240 is 1026, which is what we want mod 1000, right? So just 026, I guess. And 056, 057. But we should have like highlighted this. We have to multiply by 7, right? So this is pretty important because it's really easy to forget about multiplying by 7. So maybe like write like multiply by 7 on the top of your paper or something like that. That kind of stuff would always help. What am I doing? 57 times 7. 399. So the answer is 399. So yeah, clear audience. Yeah. Oh, oops, I made a typo over here. But yeah, I also wrote like a sketch walkthrough. And yeah, you can refer to this if you want like a general view of how to do this. All the details. Anyways, let's go to our next example. Find the number of functions f of x from 1, 2, 3, 4, 5 to 1, 2, 3, 4, 5 that satisfy f of x is f of x for all x in 1, 2, 3, 4, 5. So, as always, we draw it out. The drawing might be a little more messy because there's 3 iterations of f. But yeah, 1, 2, 3, 4, 5. It's also nice because 5 is a small number. So you don't have to like draw 1, 2, 3, 4, 5, 6, 7, 8, stuff like that. Yeah. So f of x is f of x. So one thing you might want to do is let y equal f of x. Oops, this is horrible handwriting. F of x. 1, 2. So this means that y equals f of y. So for all y in the range of f, which is this is the image of f, like, but that means range of f, y equals f of y. So a natural thing to do is do image of f of x. Oops, not image of f. Okay, so this is true. So a natural thing to do is casework on the image of f of x. And more importantly, how many elements it has, because it really doesn't matter if it's like 1 instead of 4, it's the really symmetric. So anyways, casework. This one is even more casework than the last one. So at least we have like a lot of room. We can even like work on here. Can we even work on here? Like this? I guess we can work everywhere. Anyways, so let k be the number of elements in the range of f of x. The reason I'm running image instead of like range is because like there's no like notation for range. It's and people just use image, I guess. Like no, there's no like array. So just like for shorthand, I guess. It's also cool to know that image is also another word for range, I guess. Anyways, so let's say the size of this is 1. The size is okay. So the size of this is 1. So that also generality let the 1 that all f of x maps to is just 1. So we have 5 choices, and we want f of x to be constant at 1. This seems familiar to the other problem, and I guess we already know how to handle it, right? And indeed, it's the same exact thing. So f of 1 is 1 by the same logic as before, right? If you need a refresher, f of 1 equals 3, or something else would imply f of 3 equals 1. But that means f of 3 equals 1 and f of 1 equals 3. But everything has to map to 1. So 5 times. So again, we do like mini casework on how many things map to 1. So let's say L of them. So L of these map to 1. So L of them, right? Then there's 4 minus L of them remaining. And by similar logic, as the one problem. Wait, it was the problem above, or was the problem above that? I think it was problem above, right? So 4 minus L of them map to L of them. So first of all, there's 4 choose L choices, right? For this thing, we go to that, and they're L to the 4 minus L choices for these to get distributed, I believe. So, and L can range anywhere from 1 to 4. So sum L equals 1 for 4 choose L. L to the 4 minus L. So L equals 1. So we just compute this out. 4 choose 1, 1 cubed. 4 choose 2, 2 cubed. 4 choose 3, 3 cubed. And 4 choose 4, 4 cubed. So 48. 27 times 4 is 108, I believe. 64. 52, 160, 224. Like this is too big. Is it? I mean, this already gives an. Hang on. 4 choose. 4. Okay, this is 48. So 52. 27 times 4 is 108. 160, 224. But yeah, this is too big. Oh, oops, I'm so dumb. Never mind. Actually, this should be 2 squared and 3 to the 1, right? 4 minus 1 off L to the 4. So yeah, this is way smaller. Never mind. So this is 4. This is 24. This is 12. And this is 4. This is 28. This is 40. This is 44. 44 times 5 is 220. So 220 plus 4 choose 1, 1 cubed is 4. 4 choose 2, 2 squared is 6 times 4 is 24, 28. 4 choose 3 times 3 to 1 is 12. Oh, this should be 1. Never mind. Oh. Yeah, I felt something was off because like I did this like a few minutes ago. And I remember getting something off this. So 452, 160, 160. No, not 160. But I should have probably write these again. 4 plus 24 plus 12 plus 1, 28, 40, 41. 41 times 5 is 205. So case 1, 205. And there are more cases to go. So we should probably write down for case 2, case 3, case 4, case 5. Okay, so case 2 is when this maps to 2 elements. So 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. So let's say also, yeah, we actually didn't even need like 1 maps to 3 maps to 3 because like we already have y equal to y for y in range. So this is just immediate, right? Anyways, so let's say, so we have to multiply by 10 first of all, because 5 choose 2 for like 2 things that work. So 10, and let's say they're 1 and 2, right? So f of 1 equals 1, f of 2 equals 2. I think this is actually useful then, because like I think we can also have like 2, 1, 2 or 1, 2, 1, right? And those would also work, but they wouldn't satisfy this. Anyways, so we do like mini case work again. So, but we don't have to like write as a summation because it's only 3 terms. I don't know why I did that over there, but like, anyways. So let's say one of them let's call like this part, right? Like the railroad. I mean, the left and railroad, because like these look like rails. So let's say like let's say one of them goes to the railroad immediately, right? So we can there's 3 choices for one of them, right? And for this, let's say like we pick 3, then there's 2 choices for which railroad it goes on. So let's say it goes on this. Then 4 and 5 have to go to 3. So there's 1 choice for that. So now let's say that there's two things that go to the railroad. So 3 choices for that. 2 squared for where 4 goes. And 5 goes to either 4 or 3. So 2 choices for that. And finally, if all of them go to the railroad, there are 8 choices, 2 cubed. So what is this? 6 plus 4, 24 plus 8, 38. So 380, I believe. 380. Case 3. This is when okay, so this is when it's like 1 1 1 2 2 2 3 3 3 4 4 4 5 5 5. So 1 goes to 1, 2 goes to 2, 3 goes to 3, and so oh yeah, we have to multiply by 10, right? Because we choose 1, 2, and 3 from 5. 5 multiply by 5, choose 3. And then 4 and 5. Let's say one of them goes to the railroad, and at least one of them must go to the railroad, right? Because how else are they going to reach at 1, 2, or 3? So let's say one of them goes to the railroad. 2 choices for which one? Let's say 4 goes to the railroad. 3 choices for that, and 1 choice for 5 to go to 4. And let's say they both go to the railroad. 3 choices for each, so 3 squared. 6 plus 9 is 15. 15 times 10 is 150. Case for 4 of them. And 5 just has 4 choices. I think, great. We got a 1, 2, 3, 4. And finally, oh yeah, but you have to multiply 5. I keep on forgetting. Multiply 5 because, you know, like you want to choose which railroads there are. So 20. And case 5, all of them they're just one case, right? It's like there's one. So adding these up, 585, 150, 735, 755, 756. So the answer is 756. Also, this is like really easy to see. I think the first time I did it, I got like 751 or something. Which is like, yeah. It's pretty easy to silly most of these. So be organized, I guess. Anyways, all clear. And stop annotating. Yep. Yeah. So this is like a very basic sketch. So so we're done with all the problems, but I got another problem that I was working on like a few months ago. I silly it at first because these are really easy to silly, but I thought this was really interesting. You could try it if you want. Despite it's like number 7, like it's way harder. Like if it was on actual, it'd probably be like number 12, like these days. Yeah. I could. I'm not gonna go over a solution now because this video has already been pretty long, I guess, and I want to leave you some homework and something to think about. You can check your answer with, like you can find this mock on APS, just like search for 2018 mock combo Amy. The creator is like Amy12345, I think. And yeah, you can also DM me if you want hints. But yeah, if you don't want, I'm gonna give you guys one hint. So if you don't want it, you can like pause it and like leave later and just think about it. But if you want it, just a warning, so you can leave right now. But I'm just about to say. So one thing you can do is like this is like different from all other combo problems. You can like the other ones we just did. You can actually like use recursion, which is not that common in these function finite problems because there's like weird stuff, right? Like I remember like from like which one? No, not 2018. This one, right? There was like and this one. There was like a to the 4 minus a. Like these are not like recursive things. with this one, you can actually like use recursion. Like I don't know that way other than recursion. There isn't an official solution. So I mean, yeah, but this is really interesting. And again, just draw around. It's like just draw. And these are actually pretty fun. I didn't realize how fun these are. Like just like drawing around. Even the casework, even though the casework is actually these are really fun. Anyways, I was gonna say, yeah. Good luck on the Amy. I hope you found this instructive. I don't think there's a handout corresponding with this, but I don't think there's a handout corresponding to any of the other videos if I'm correct. And I guess I'll just cut it here. So good luck on Amy. Bye. And